Hi, this is Mr. Shumway. This video clip explains how to predict the final temperature of objects at different temperatures placed in a single system. So if they arrive at a single temperature, we predict what temperature that will be. So let's give an example. If we put 2 kilograms of steel that's at 45 degrees into 1 kilogram of water at 5 degrees, what will the final temperature be? Well, we know that the heat gained by the water will be the same as the heat given up by the steel. So heat transferred to the water from the steel, although one will be a negative sign, one will be a positive sign, their magnitudes will be the same. Okay, well, heat transferred to the water is the heat capacity of water times the mass of water times the change in temperature of the water. And that same thing is true for the steel. Heat capacity of steel times the mass of steel times the change of the temperature of the steel. Now, I have to be a little bit careful about the change of temperature of the steel so that we end up with a positive number in both cases, so that doesn't confuse us, because the magnitudes are the same, but the values are opposite in sign. So the water starts out cold and gets hot, so let's take the final temperature, which is warmer than the initial temperature, and so that subtracting will get a positive number there. And if we take the steel will be initially hot and then it will cool down, so if we subtract in that direction, that will be a positive number also. So the change in temperature, I guess we could do an absolute value, but either way. So I'm going to go ahead and multiply what's outside the parentheses, so to get rid of the parentheses. So I have two terms on each side of the equal sign. Now I'm going to add what's in blue to each side of the equation. As long as I add the same things to both sides, hopefully you believe from algebra that it will still be equal. Either side, both sides will still be equal. The reason I added those particular things is because that one is positive, one is negative, they cancel. And here I have one is positive, one is negative, and they cancel. So I only have two terms on each side now. And it just so happens that I have a final temperature is common, a common factor of both terms there. And so I can factor that out. And if I do that, then I have what's in parentheses times that. So to isolate the final temperature, all I have to do is divide by what's in parentheses. So let me just underline what's in parentheses and where it is over here. So I have divided both sides by that. On the left-hand side, it cancels. On the right-hand side, it stays. Well, all of those things we can measure. We can measure the mass. We can measure, well, we can look up the heat capacity in a table. We can measure the initial temperature. We can look up the heat capacity of water. We can measure the mass of the water and the initial temperature of water. And so everything on the right-hand side we can either measure or look up in a table, and so we can predict what the final temperature will be. So replacing those variables with values, heat capacity of steel is about 450 according to some texts. Heat capacity of water is about 4,200. 2 kilograms of steel, 1 kilogram of water. Initial temperature of 45 for the steel, initial temperature of 5 for the water. Anyways, plugging in those numbers predicts the final temperature of 12 degrees. So when you do that on your lab, do the prediction first. Well, what you can do that, so you need to see what all measurements you need to get, and then you can do these calculations while you're system is stabilizing, when the two are arriving at the same temperature, it may take about 5 minutes for them to become the same temperature. And try it, and then you'll have that number, and then you can see if that matches what temperature the system ends up at.